Okay, so the last video was optional. I'm going to assume that you didn't watch it, so we're going to summarize real quick before we proceed. In the beginning of the 1900s, we thought there were only 4 more mysteries to solve in science. Seriously, that's what we thought. And that if we could just answer those 4 last mysteries, we would have a unified theory for the entire universe, for how everything works. Those 4 mysteries resulted in some observations that are kind of important. The first one is that light is quantized. That means light has to behave as a particle, as a discrete piece of something. Some of them also concluded, like line spectra, that light has to behave as a wave. And those 2 things are exactly opposite in math, okay? If something behaves as a wave, we have a certain set of rules that we can use to dictate how it's going to work. That's called wave mechanics, and that's a math field, okay? An area of mathematics. If something behaves as a discrete particle, that's a different area of mathematics, which is mostly what we have worked with, algebra up until you get up to calculus. Everything is discrete mathematics. But our results, our observations, our conclusions from those 4 mysteries lead us to both of those conclusions being true. They can't both be true under Newtonian physics. Okay. And there was another mystery that I didn't include in the last video, which I really like, so I'm going to just tell you briefly. It's called the UV catastrophe, which is the best name ever. But it's kind of related to black body radiation that I spoke about a second ago. Think about your stove and how your stove heats up, and you can tell it's hot because it turns orange or red. The UV catastrophe is that if you keep heating something up past purple light, it will start emitting UV energy. Newtonian physics calculates that the amount of energy required to make something emit UV radiation is infinite, like literally an infinite amount of energy to make UV light. And yet, we know that the sun produces UV light all the time, so it must not be true. You can't have something require infinite energy and have it actually occur, because the law of conservation of energy cannot be violated, right? And infinite energy would definitely violate that. So anyway, here we are with all these mysteries, and none of them seem to agree with each other, and we can't make a unified theory of everything. And it turns out, even though we have solved these mysteries, we still can't make a unified theory of everything. We're closer, but we can't. Because things on the atomic level don't behave the way we would expect them to. So, all of these phenomena lead us to a couple of equations where we can treat energy as discrete levels. So that uses Planck's constant, which is just a value you look up. Okay, don't get too excited about having to memorize it. Don't do that. It'll be on your test. It's fine. And we also have equations to relate the speed of light, which again is the variable c. Quick reminder, lambda is wavelength, and nu, the one that looks like a V, is frequency. Those are the symbols we use. All right, and so c is also provided to you, but it's 2.99 times 10 to the 8 meters per second. That's the speed of light in a vacuum. That's what we use. So we get all these equations from it, and we can treat it as a wave or as a particle, and we get different answers from both of those perspectives. What we wanted was a way to unify them. So something called the wave-particle duality was created, invented, and that is the beginning of quantum mechanics, right? And so quantum mechanics is actually, it gets a bad rap because it sounds really scary, but it's actually really, really interesting. And without it, you would not have a cell phone capable of doing what it can do today. You wouldn't even have a laptop capable of what they can do these days. So we're going to understand a little bit of the quantum nature of the world, because it's going to set you up for future work in science, but also because it's just really interesting. It leads us also to a discussion about how molecules are shaped, which gives us a way to discuss how reactions occur. Okay. I'm gonna skip this slide. It isn't a student learning outcome that we have to know, but it is just an interesting fact. This is the math that was arrived at to explain that line spectrum of hydrogen. And so essentially, if you put whole numbers in for n, where you want to get a positive number from this parenthetical here, so n could be 2 here, but it could be 3 over here. You get a positive number out of that. You can calculate the wavelength of light that would be emitted when electrons jump between different levels. And that's what causes the line spectrum of hydrogen to exist, because there are different energy levels that the electrons can be at. Okay, and so you can picture that kind of from a Bohr perspective, right? So the center here is our nucleus, and each ring represents what Bohr called an orbital. And this comes from the Saturnian notion also. But essentially, it just says if an electron goes from energy level 3, so this is our nucleus, here's energy level 1, here's energy level 2, and here's energy level 3. So if an electron goes from energy level 3 down to energy level 2, it has to lose energy to do that. When electrons go down in energy level, they must emit light. We must give off light to do that. So that would be like the blue arrow here. When you go from a high energy to a low energy, you're going to emit light. If you go the other way, so if I shine that same color of light onto the atom, the electron will absorb it, and it will jump from the ground state up to a higher energy. We call these all excited states. Okay? The farther from the nucleus you go, the higher in energy things are. So you can think about it as a vertical diagram, but remember that has a 3D meaning as well. All right, so if we go from 3 to 2, we're going to release energy in a certain color of light. In particular, and we can go back in the equation and do it, but you get blue light when you go from 3 to 2. Okay. So we have some vocab terms here. Ignore the animations. There we go. We have some vocab terms here that are important to understand. Ground state is when all the electrons are as close to the nucleus as they can be. An excited state is when one or more electrons are not as close to the nucleus as they can be. All right, so the nucleus is like the center of our atom, of course, and the farther electrons are from that, the higher energy they are. All right. So I'm going to skip these transitions as well. This isn't a required part of the course, so I took it out. But again, for those of you who are studying physics or chemistry, it's really interesting. Come talk to me in office hours about it. All right. Those calculations that I went over are summarized, or that I skipped rather, are summarized here. Okay. So the 3 to 2 transition is actually red. I misspoke earlier. I said it was purple. It's red. And the 4 to 2 transition will give you the indigo color that physicists don't want me to use. So as you might guess, 5 to 2 gives you this light purple, and 6 to 2 gives you the darker purple. So you'll notice, remember, wavelength and energy are opposite of each other. So that means the red color, being a higher wavelength, has a lower energy. So we'll go from 3 to 2, and it'll produce red. It's a smaller gap, right? And then to go from 4 to 2 is a bigger gap. So we're going to produce higher energy light. 5 to 2 is even bigger. And 6 to 2 is the biggest yet. So that's going to have the biggest gap and produce the highest energy, which means the lowest wavelength. All right? A lot of people think the red side is higher energy just because that's what we affiliate with things that are hot. But actually, UV light is higher energy. Okay? So, the good news is, Bohr's theory and the Rydberg equation and all the math that I skipped over explains these precisely for hydrogen. You can put in any values of n and calculate what wavelength of light is going to come out of that. And that's great. So Bohr thought, okay, we did it. We figured out line spectrum. We figured out how light can be a particle and a wave. Here's the equations. We're good to go. So he publishes his paper. Oh, but wait, there's more. So just as he thought he solved the problems, it turns out that Bohr's, all these formulas can only calculate the values for hydrogen atoms. And that's because hydrogen atoms are the simplest, right? One proton, one electron, that's it. So those are pretty simple systems. But when you go up to helium, now you have 2 protons, and so 2 electrons. And electrons repel each other because they're both the same charge. And so do protons. And so things get muddy after that. When you have more than 1 electron in a system, it gets confusing. Also, Bohr's model does not explain why electrons just don't fall into the center, right? I just said electrons are negative and protons are positive, and positives and negatives should be attracted to each other. So how come electrons don't just crash into the nucleus and make atoms smaller? Bohr's model does not tell us why. Also, it really doesn't integrate the wave nature of light very well, even though the original observations require light to behave as a wave for a diffraction grating to separate them into a rainbow. There's no other explanation for it. But his math is treating it as a discrete particle. So then our friend de Broglie comes along, and he also realized that the size of the particle would impact the wavelength. So in Bohr's model, he was only thinking about electrons, which are assumed to all be the same size regardless of where they come from. But de Broglie realized, well, what if we had other objects? Something bigger than an electron, like a proton, or a neutron, or a baseball, or an elephant. Okay, I'm going to put up a TED Talk that you're going to look at in a little bit, but basically, the conclusion from de Broglie's work is that everything has a wavelength. We can't always measure it, we can't always perceive it, and it doesn't always emit light that we can see, but everything has a wavelength. Elephants, baseballs, people, cars, protons, neutrons, quarks, everything. Okay, so I'm going to embed these as questions for you to answer, and I want you to give them a shot in Blackboard. The equation is here. Don't forget to look up Planck's constant. Okay, and solve this. Remember that your units have to cancel. That's the main key here. Just like in chapter 1. So now we use electrons to visualize the microscopic world. And up until about 2 weeks ago, this was the only way to see things down at the atomic level, was to shine electron beams. And by the way, to make an electron beam that's big enough to do this, you have to have a microscope that is literally the size of an office, all right, like a room, okay? These are big, and they're really, really tall. But we can shine an electron beam on objects, and we can get very, very detailed representations of them. These are colored by an artist. When you get the microscope images, they're all in black and white, kind of like the middle one. This is the nano car. It was one of the smallest, it's no longer the smallest, but it was one of the smallest mechanical objects ever created. And it was so small we had to use an electron microscope to see what it even looked like. So I think this one was made with subtractive manufacturing for you mechanical engineers. But others have been made since then on the atomic level with additive manufacturing, where you just literally put in an atom in each place that you want. You add them together until you get the shape you're looking for. This one, of course, is a fly. It has been colored by an artist to give us the ability to sort of make sense out of it, because there's so much detail in here that it confuses the eye when it stays in black and white. And of course, this one, in celebration of our beginning of winter, is snowflakes, right? And so snowflakes all have different shapes as long as they're mature. We'll learn about that in chapter 12. But they all have kind of a similar structure. They all have a hexagonal structure. And so this is all knowledge from electron microscopes, which depend upon quantum mechanics and both the particle and wave nature of light, and how electrons can be excited, and it's just all such cool technology. Now, our friend Heisenberg. I'm actually going to have you watch a video about this. So it's a TED Talk. Take notes on it and try to understand the idea of uncertainty as it relates to momentum and position. But this is the equation.